All right, so we would like to introduce 4.3 today. And we are in this chapter about probability. And so the first couple sections of chapter 4 started with an introduction to the basic concepts of probability, and then looked at the addition rule and multiplication rule. So there was a lot of notation like P for probability, A and B representing a particular event occurring, and how to write P of A, meaning the probability that event A will occur. And these things quickly can become overwhelming unless you've had a lot of exposure and practice and discussions about them. So the symbols can really become overwhelming, and that's probably going to definitely hit the case for us in today's section 3, in which we're going to look at complements and conditional probability and Bayes' theorem. So in this introduction, I'm going to try to use examples as much as possible to give extra illustration to what they're showing us in the images of the slides, because I think the notation heavy use and the formulaic mathematical sort of algebraic approach to working with probability is very impenetrable unless you've had a lot of time to spend with the material. And who of us have had that? All right, other than me, of course, I'm the teacher. All right, so anyway, at any time, if you are willing, try to come up with your own examples in your imagination. If you're willing to share them, that's great. If you're feeling completely overwhelmed, you can watch the video later, but we are gonna give it our best shot today. All right, so having said that, key concept. We extend the use of the multiplication rule, which was in 4.2, to include the probability that among several trials, we get at least one of some specific event. Again, now they're talking in general, and it's really hard to think about general statements that are broad if you don't know clearly what they're referring to or what their meaning is. So what do they mean by several trials that you get at least one of some specified event? So here's a simple example. My trials or my procedure is I flip a coin to see if I got heads or tails. Several times of doing this might be that I flip it 5 times. And of some specific event, the question would be at least one. If I flip a coin 5 times, did I get at least one heads? As an example. So the possibility that I get heads on the first try, well, then I already got at least one. It doesn't matter what happened after that, but lots of stuff still happens after that. Or maybe I get tails, and then on the 3rd time I get heads. Or on the 4th time I get heads, or who knows, maybe they're all heads. So at least one would be at least one heads. There's lots of ways that that could happen. In fact, the only way that I could not get at least one time that I got heads would be to never have gotten heads at all, which means I got tails all 5 times. Tails, 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 tails. So calculating the probability of getting at least one heads can initially sound like a very complicated thing. But actually, we're going to use something we talked about in 4.2 called the complement rule to get at that calculation result in an easier way. And that's one of the things they discuss as a key concept in this 3rd section of chapter 4, as well as some other things. It also says we consider a conditional probability, which the symbols were reduced in 4.2, but we're going to use it and work with it more in 4.3. A conditional probability is the probability of an event occurring when we have additional information that some other event has already occurred. And we provide a brief introduction into Bayes' theorem, which we may not get to in the slideshow today. So a conditional event in the example I was just discussing is, let's say I flipped a coin twice. And the one event is that I got heads on the first flip or the first toss. And that's another event is that I got tails on the second toss. So we could ask for a conditional probability by saying, what is the probability that I get tails on the second toss if I know that I already got heads on the first toss? So that's a conditional probability. I'm asking for the probability of tails on the second, conditional on the fact that I already know that, or I'm assuming that I got heads on the first toss. How would that give my probability for the second event? And I'll give you a simpler example that's less mathematical. I could ask, what is the probability that the ground will be wet tomorrow, given the fact that it rains? So you could see, given one event having occurred, could drastically affect the probability of an event that seems related, that seems like it would have an impact. Or it might be that there's no impact at all. So for example, the probability that I get tails on my second toss of the coin isn't really affected by whether I got heads on the first toss, because it's a totally separate toss. And those aren't really related. Those are, as we would say in 4.2, those are independent events. One doesn't have anything to do with the other. And so the probability isn't impacted by the earlier event. But the probability that the ground is wet tomorrow goes up a lot if it rains tomorrow. It doesn't have to rain. Ground could be wet because maybe I was out watering plants and I spilled a bunch of water and the ground was wet. But certainly if it rains, there's a good chance the ground's going to be wet when I check it out. So this is the idea of a conditional probability with some simple examples to imagine trying to discuss and think about these things before we get too much into the symbols. The symbols very quickly are going to be overwhelming. The notation, the mathematical approach to things, they're going to be very challenging. And so as students, I think the best defense on being overwhelmed by that is to go slowly and carefully through it and trying to illustrate these general statements and symbolic meaning of things with examples as best as we can. So let's move past the key concept, see if we can begin this process. Complements the probability of at least one. When finding the probability of some event occurring at least once, we should understand the following. At least one has the same meaning as one or more. So at least one is 1, 2, 3, 4, 5. At the very least one, but could be more. So one or more. The complement of at least one particular event is that that you get no occurrences of that event. The complement of getting heads at least once is that I never got heads when I was flipping a coin multiple times. The complement of having 5 kids and having at least one girl, the complement of that would be that you had all boys. Now, again, the word complement, if that's hanging you up, that's in 4.2. The complement of something happened is that it did not happen. So the complement of at least one means that you did not get at least one, and that's why the only way to not get at least one is to not get any at all. And that's why they're using the word complement. It's in bold, but they did define that in the previous section. So there was a rule from the last section that if you have an event A and the complement of event A, first of all, in the notation, as we see here, is this bar over the A. If you draw that line across the top of the A, that's referred to as A bar. It means the complement of A, or logically, it means that A did not happen. So you can think of it as not A. So if A was that I got heads when I flipped a coin, then the complement of that was that I did not get heads when I flipped a coin. And since there's only 2 possibilities, that would mean I got tails instead. If I am picking from a bunch of numbers from 1 to 100, and the event A is that I pick a number between 1 and 10, then not A would mean I did not pick a number between 1 and 10, meaning I picked something bigger than 10. So if the event A is getting at least one of something to have happened, then not A means you did not get at least one. So the complement of A is that you didn't get any at all. So that's the A is equal to getting none of the event being considered. All right, so that's just setting up notation and language and the idea. So to find the probability then of something not happening, well, the complement rule from 4.2 said that something either happens or it doesn't. That's a certainty. If it occurs or it doesn't occur, one of those has to happen. So the complement of, so those two things together must happen and must therefore have probabilities that add up to 1. If there's a 30% chance that I get a particular result, then the other 70% of the time I don't get that result. And those add up to 100%. The probabilities add up to 1. And if I know one probability of event, then I know the complement because I know they add up to 1, so I can just subtract. If there's a 20% chance that it's going to rain tomorrow, well, then that means I also know there's an 80% chance that it won't, because those have to add up to 100. The probabilities have to add up to 1. So to find the probability of A complement or A bar, that's equal to the probability that A does not occur. So we can subtract the result from 1. We can subtract the probability of no occurrences from 1 to get the probability of at least 1 occurrence. So again, a bunch of stuff written here, making it very confusing. Let's see if they give us an example that's nice. Let me do one first that's more in line with what we've been discussing, because theirs will be probably a little more confusing. So earlier on, we were looking at the sample space of having 3 kids and considering which genders we got. And there were 8 possibilities, like boy, 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 girl, girl, boy, et cetera, et cetera. There's 8 different equally likely outcomes for having 3 kids and what gender we get. So we could say, for example, what is the probability with having the 3 kids of at least 1 girl? So what they're saying here is that that would be equal to 1 minus the probability of no girls. And so instead of having to count up all the different ways that I could have at least 1 girl, I can realize that there's only one way to have no girls. Boy, boy, boy. And that's 1 out of the 8 different possibilities. And that means 1 minus the 1 out of 8 ways that I can have no girls would be the other 7 out of 8 ways that I had at least 1 girl. 1 or 2 or all 3. And so here's an example showing the calculation they're talking about here in a situation where we could maybe see that from an earlier example that we used. Questions, comments, discussions about this at this point? All right, so the big thing they're doing is 2 things. If you know the probability of one thing happening, then the complement will just be 1 minus the probability of that thing happening. Then they point out that if you want the probability of getting at least 1 occurrence of A, then that's going to be 1 minus the probability that A never happened. And that oftentimes that's a much easier calculation. So if I want the probability of getting at least 1 girl when there's 8 different ways that I can have results, well, that's 1 minus the probability of no girls, which is a 1 out of 8 possibility. And so I take 1 minus 1 out of 8 and I get 7 out of 8. All right, let's see if their example is also helpful. They devote 4 slides to it, apparently, 1 of 4. A study by Square Trade found that 6% of damaged iPads were damaged by backpacks. If 20 damaged iPads were randomly selected, find the probability of getting at least 1 that was damaged in a bag or a backpack. At least 1, that means 1, 2, 3, 4, 5, 6, all the way up to 20. Maybe all 20 were damaged in a backpack. Is the probability high enough so that we can be reasonably sure of getting at least 1 iPad damaged in a bag or a backpack? Well, there's only a 6% chance that an individually picked iPad will have been damaged that way. But out of 20, does that mean you're going to get it, that you should expect to get at least one? That's really the question here. So some of the things to think about, and then the slides I'm sure will show us, that if I'm trying to get the probability of getting at least one, that's the chance that 1 out of the 20 or more were damaged in a bag or backpack. So that could be 1 or 2 or 3 or 4 or 5 or all the way up to all 20. And so there's all those different ways that you could get at least one, and trying to figure out all those probabilities and total them all up is much more work, because the probability of at least one is 1 minus the probability that none of them were damaged that way. And that's a much easier thing to calculate. So that's the concept. Now let's see how they approach this. So they're going to assign some symbols so we can talk about this mathematically. Let A equal the event that at least one of the 20 damaged iPads was damaged in a bag or a backpack. This is not a simple event, because there's lots of different simple ways that you could have at least one be damaged that way, because it could be more than one, and lots of different ways that could happen. Step 2, identify the event that is the complement of the one we just defined, A. The complement of at least one of the 20 is that not at least one, meaning none of the 20. Not getting at least one is that all 20 were damaged in some other way, not while in a bag or backpack. There's only one way that can happen. Every single one of them was damaged in a different way. All right, so with that in mind, how would we calculate that? Again, this is going to use something from 4.2. So if there's a probability that something is going to happen and you repeat that procedure again and again, each time it faces that same probability, if these are independent events, and the probability that happens every time, you would multiply all those probabilities together. And so it says, to find the probability that all 20 were damaged not in a backpack. First of all, if the probability of being damaged in a backpack is 6%, then the probability of being damaged not in a backpack is 94%, because that's the complement. Either it was in a backpack or it wasn't. And if 6% were, then the other 94% were not. And to randomly choose one when 94% are not damaged that way, that's an individual thing. But then when I choose one again, there's another 94% chance. And to have done that all 20 times, you multiply all of those percentages together. And so they're illustrating that here. So they're basically saying the probability that all 20 were damaged in a way other than a backpack. So reminder, this is the probability of one iPad damaged not in a pack. And then to get all 20 of them, you have to multiply together 20 times. So they get this calculation of 0.94 to the 20th power, meaning times itself 20 times, and then they get this result here of a little bit less than 30%. Now, that's the probability that all 20 would not have been damaged in a backpack. That means the complement that all 20 were not damaged in a backpack is that at least one of them was. And that's the probability we're actually looking for. So they use this complement rule from 4.2, and they subtract none in a pack. They subtract the probability that none were in a pack when damaged from 1, and that gives them the probability that at least one. was damaged that way, which is what we were looking for. So if 29% is the likelihood of having none of them damaged that way, then 71% is the likelihood that at least one of them was damaged that way. Questions, comments, discussions while we have this slide up?
I do. I want to know, how did you get the 0.94?
So they gave us here, yeah, they didn't even show that. So that's a great question. They gave us here that is 6% are damaged by, but in backpacks. So that means if 6% is the probability of being damaged in a pack, then the other 94% were not damaged in a pack. Does that make sense?
Yes, thank you.
So when to say that all 20 were not damaged in a pack, we have to look at each one having its own 94% chance of not being damaged that way, and then combine those together to get all 20 were not. Does that make sense? Are you satisfied with that?
Yeah, thank you.
Yeah. Other questions to help provide clarity or explain things better? If anyone's willing to ask a question, I can try to elaborate.
I have a question.
Yes, please.
How come you multiplied 9.94 by itself 20 times instead of just multiplying it by 20?
Good question. So first of all, let me point out, just to help you remind ourselves that we are talking about calculating a probability. 0.94, that's like a little less than 1, right? If I multiply that by 20, what kind of a number would I get?
More than 1?
Yeah, kind of close to 20, right? Maybe like 19 or something like that. Can that be a probability?
No.
Right. So the first thing to recognize is that when you're combining probabilities together, it's very rare that you can just add them up, especially if when doing that, you'd end up with more than one. Now, the time when you can add them up is when each one is some amount out of a total, like 2 out of 100 plus 7 out of 100. Then when you add those up, as long as the things you're adding can't exceed all 100, then you'll still get something less than 100 and you'll get a number less than 1. So it does boil down to the difference between when do I add and when do I multiply. And that's why in 4.2 they covered the multiplication rule and the addition rule. And so here's a way we can see it in our simple example here. Let's say I had 2 flips of a coin. Let's change colors here. And I'm going to designate the results I get with these boxes. So you see I'm drawn on the screen here. So I can get heads or tails for the first flip, and I can get heads or tails for the second flip. Is that showing up on your screen?
Yeah.
Okay. All right, so let's use this simple example for you to sort of sort out in your mind, because once we get up to 20 and these decimals, it's just overwhelming. So what is the chance that I get heads on the first flip?
Would it be 50%?
50%, right? Doesn't matter what happens in the second one. First time I flip it, do I get heads or tails? 50%. I'm going to write that as 1/2. So to get heads, I have a 1/2 chance on that first flip. What is the chance on the second flip that I also get heads?
Would it still be 50%?
It is, because the second toss has nothing to do with the first toss. You're still flipping a coin, and there's 50 heads, 50 tails. So now if you imagine trying to combine those together in this simple, more graspable example, and you were saying, well, what is the chance that I get heads twice? And the two default operations you have to think about, do I add those individual probabilities together or do I multiply those individual probabilities together? If I add those two 1/2s together, what do I get?
1/4.
That's not if I add them.
1.
I would get 1. If I add those two probabilities together, I get 1/2 plus 1/2, which is 1. So the conclusion would then be that the probability of getting heads twice is 1, but 1 is supposed to be a certainty. And you know it's not certain you're going to get heads twice. Then if you compare that to what the first answer was, what if I multiply those two probabilities together? 1/2 times 1/2 is 1/4. And that makes more sense because you can even visualize that there are 4 possibilities. There's heads, 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 tails, tails, heads, or tails, tails. And only one of those 4 did I get heads both times. So I'm using this simple example because as you're trying to sort out the confusion between when you multiply and when you add, if I have 20.94 occurrences, the question was, well, why don't we just multiply that by 20? So if I simplify it down to saying, well, I have 2 occurrences that are each 1/2 of a probability, why wouldn't I just multiply that by 2, which means add the 2 together? Well, 2 times 1/2 is 1. So at least you could see in a simple example, does that make sense as the result you would get with the question you were asking? If you want all those individual things to have occurred, then you multiply their individual probabilities together. And remember that for multiple things to have all have happened, that's harder than for any one of them to have happened. It's harder to get heads both times than to just get heads one of the other times. And when you multiply numbers together that are less than 1, the result is always smaller. In this case, we can see if I multiply the two 1/2s together, I get 1/4. And quickly we can see that makes sense because only 1 out of 4 of the possibilities would be that both times he got heads. So what we're comparing here is when you have a succession of events, each has their own likelihood of occurring, and then you want to know what's the chance that they all happened. That you're either thinking about, is this a time when I would add the probabilities together versus is this a time when I would multiply the probabilities together? And thinking of a simple example where you can consider the 2 results and whether it makes sense or not, hopefully will guide you so that when things get more involved and complicated, you can still have the same ideas driving your thought process. Are you satisfied by that?
Yeah. Thank
Anybody
you.
have follow-up questions, comments, discussions about this? And I just want to compliment Mila, I guess, I think it was. The best question you can ask in any class, specifically in math classes, is not what did you do, is not how did you do that, but why. It was shown that you multiply these together and you get this number raised to the 20th power. Yes, this is being recorded. And then asked, why don't you just multiply by 20? And so I just want to compliment that because it's a harder question to ask. Many teachers find it harder to answer. Many students don't have the energy to ask why because they're just trying to deal with how it was done. And it's hard to find the energy to pursue that additional line of query, of inquiry. But it's usually the one that really helps sort things out. And if you ever have a teacher that says, you know, I don't really know how to say why, just do what I'm doing, don't let them get away with that. Make them explain why if you're ready to hear why, because that's the hard part, but that's the important part. That's the part that lasts. That's where you start to understand it. So hopefully this was helpful. I'll move on from this mess. There is another slide here that they're going to give us. the interpretation in this fourth slide of this example, for a group of 20 damaged iPad, there was a 71% probability of getting at least one that was damaged in a backpack. This probability is not very high, so it's reasonable. You can be reasonably sure of getting at least one, but it's no certainty. Questions, comments, discussions about that example? Okay. So now conditional probability. A conditional probability of an event is a probability obtained with the additional information that some other event has already occurred. And as I was discussing earlier, by looking at that, it may then call into question whether the first event occurring has any impact on the probability of the later event occurring. Like the ground being wet tomorrow if it rains. Versus the second coin toss being heads if I know the first coin toss was heads. The crux of this will be whether the events are independent or dependent, which again was defined in 4.2, and we'll try to re-illustrate that idea as it relates to conditional probability here. So this is the notation for that, which they did also throw at us in 4.2, but nicely they're reminding us of it here because they didn't do much with it in 4.2. So this is read as the probability of B given A. So let me write that. Well, I guess it's right here. Is the probability of event B, I've got to get a pen here, given that event A has already occurred. And so the short that is when you read this, this is read as the probability that B happens given that A has happened. All right, so again, general discussion with no specifics is very hard to follow. And then another slide where they couldn't manage to recognize that the second parentheses was going to somehow miss the mark. There's a parentheses over here. So the intuition behind this idea of the probability of B given A, the probability of B occurring given that A has already occurred can be found by assuming that event A has occurred and then calculating the probability that B will occur, which kind of makes sense. But what does that mean in terms of a calculation? If they don't show an example, I will. They are showing a formula. All right, so I will. So let's use the coin toss example that I just gave. So you toss a coin twice, and there's 4 possibilities, which I'm quickly drawing here. So let's say A is first toss was heads, and B is the second toss was tails. So if I write the probability of A, so I would look at, of those 4, how many had the first coin toss be a heads? And this would be 2 out of the 4 possibilities. On the top 2 had heads first. And of course that simplifies to 1/2. And it's not too shocking that when you flip a coin the first time, the chance that you get heads will be 1/2. The probability of the second event occurring is that the second result was tails. So that happens here and here. Again, that's 2 of the 4 possibly equally likely results of the 2 coin tosses had the event occur that the second toss was tails. And so again, that simplifies to 1/2. And it kind of makes sense. When you flip that second coin, there's a 1/2 chance it's going to turn out to be tails. But using this new concept and this new notation, which I just ran off the top of our screen there. So then the probability of B given A, what does that mean in this context? That's the probability that the second toss was tails, given that you already know the first toss was heads. So when it says, assuming that event A has occurred, that means you can eliminate for consideration all the other possible events. So what that would mean in this case is that if for me to assume that event A has occurred, that means I'm going to assume that I got heads on my first toss. That means I'm going to ignore not having had that happen. And that means that this is now the only thing I'm considering. By assuming that I got heads on the first toss, I can restrict what I'm looking at to only those situations where I got heads on the first toss. And then I can calculate the probability of B, which was that the second toss was tails. Well, when I considered all the possibilities, there was 2 of the 4 of them where the second toss was tails. If I restrict that to only the ones where the first event was heads on the first toss occurred, then I'm only down to those 2 possibilities. But what we can see from those is that still the probability that I get a tail on the second one is 1 out of the 2 possibilities that are left, and it's still 1/2. So this came out the same as this because whether you got tails, heads or not on the first toss doesn't affect the likelihood of what happens on the second toss. So that's why they came out the same. But there are many situations where they won't, in which if I restrict to some event A having occurred already, then all of a sudden the probability that B occurs changes, like the chance that the ground is wet tomorrow if it's raining. If I restrict, if I think of all the days in a year and I look at the days where the ground was wet, well, there'll be a whole bunch of rainy days, but there'll be some days the ground was wet because I was watering or something like that. So there'll be some number of days out of the year where the ground is wet. So the probability the ground is wet is that number out of the year. But if I say, well, what's the probability the ground is wet if it was rainy? Well, then I throw away all the days where the ground wasn't wet on non-rainy days. I throw out all the days where it was wet on rainy days, on non-rainy days because I was watering. And I only look at the days where it was raining. But what you'll see is that on those days, almost all of them, I would think the ground was wet. And so the probability goes way up when I assume that it was raining or that it's rainy. When I make that assumption, then all of a sudden the chance of the ground being wet goes way up. Questions, comments, discussions about that while we have this little simple coin toss example up here? Goddamn math. All right, so let's see what they do for us. So they give us a little formula. The formal approach for finding the probability of B given A is that you have the formula where you do the probability of A and B on the top divided by the probability of just A on the bottom. So by dividing by the probability of A, remember, we're normally on the bottom dividing by all the different ways that anything could have happened. So by dividing by the probability that A occurs, meaning you're just considering I'm only going to divide by the ways that A could have happened, and then consider the fact that A happened and B also happened. That's the logic here. And you can see that in the math, but in the end, it's a formula. And if you understand the logic of it, the formula will make sense. And even if you don't, the formula still can be used, even if it doesn't make sense. The harder stage is to make sense of the formula. Like I said, the symbols will be overwhelming and you have to fight to get the ideas through. And so that's less important than the formula. But for example, up here, the probability that I got heads on the first and tails on the second would be 1 out of 4. The probability that I got heads on the first would be 2 out of 4. And if I divide those, I get 1/2. So this formula would work for the above example. This would have been 1 out of 4. This would have been 1 out of 2. And that simplifies to 1/2. Just in my little previous coin example, so that you could see this formula in action. All right, so they threw a formula at us, and now there's an example, and I hate to even just point this out. It's got 11 slides, and we have 5 minutes. So I wanted to sort of stop here because I went over the big concepts, and I tried to use examples that were much more thought-provoking and satisfying, as opposed to something like this that it takes them 11 slides to go over. And so I'm going to stop the slideshow here, but as I mentioned before, hopefully later as you're getting more into chapter 4, if you haven't started in there already, and you get to the point where you're ready to look at something like this, maybe you come back and watch this introductory video and we go through our simpler examples, and you've already worked in 4.1 and 4.2. Hopefully the next 25 or 28 slides that they go over could be additional help. I can just give this introduction today, I think, successfully. All right, so let's stop that. And I do want to take our last few minutes and see if we can see what a homework might look like. So if I hop over to a homework set, let's just see what we get. I didn't really look at this in advance, but let's see where we are. If I look at 34, in the wrong homework set, that's where we are. So that's still in 4.2. Jump ahead a few problems. About 37. Assuming boys and girls are equally likely, find the probability of a couple having a baby boy when their 4th child is born, given that the first 3 children were all boys. So this is a problem to not only illustrate what was discussed and what we've been looking at in this section. This is 37 from your homework. But it's also designed to illustrate that there's a common sort of misunderstanding of probability that a lot of people have. So let's say you're flipping a coin, because in this case, they're treating having a boy or a girl the same as flipping a coin. And let's say I'm going to flip a coin 10 times, and the first 9 times I get heads every time. Then what's the probability that on that 10th time I get heads? So there's a couple of feelings that people get. The first is, geez, I got heads the first 9 times. This coin is not fair. It really seems to favor heads, so I think there's a good chance that I'm going to get heads on the last one. Or in the other way, wow, I got heads 9 times. I'm really due to get tails. This is like the gambler's mentality. The cards have been so bad. I just want to play a little longer because now I'm owed good luck because I just used up a bunch of bad luck, something like that. If I got 9 heads in a row, I'm just bound to get tails on the last one. But if it's a true probability that are independent, if the earlier events aren't affecting the coin on the last one, well, then you have the same 50-50 chance on the last time that you did on the first. And if it says, as we're supposed to assume that boys and girls are equally likely, well, then the 4th boy is equally likely to be a boy or a girl, no matter what the first 3 kids were. So the probability is going to be 1/2. Anyway, so hopefully this problem also illustrates that the ideas are more important than the formulas and the notation and that stuff. And sometimes they get in the way of the ideas. Because as you can see, if that idea is clear to you about how probability works, then this problem is a 5 to 10 second problem.